Hey there, welcome back to Calc 2. In this video lecture, we're going to wrap up our work in section 11.6. I want to show you something called the root test. It's going to be the last of our convergence tests. So starting with the divergence test and ending with the root test, that's our toolbox. And then we'll move on towards thinking about power series and accomplishing our ultimate goal of figuring out how I wrote those polynomials down that approximated the sine function so well. It's been a while since I've mentioned that goal, but that's why we're learning all these tests. These series are going to come up when we're trying to learn how to write those polynomials. All right, so let's get right to it. I want to keep this one kind of short. It's just got one test. It's called the root test. I'll denote it by RTT because it's got the same initials as the ratio test. And then I want to do a bunch of examples. So without wasting any more time, let's just get right into it. What's the root test say? You take a limit, just like you do with the ratio test, but you take the limit of the nth root of the absolute value of the nth term, no ratios. Okay, but then the conclusions are exactly the same as the ratio test. If that limit is less than 1, then we have absolute convergence. If that limit is bigger than 1, your series diverges. If that limit is equal to 1, we can't say anything with this test. You have to try something else. So that's very much the same decision tree as the ratio test. You just start with a different limit. When would you use the root test? Well, you use the root test when the nth root of the terms of the series simplify nicely. Let's look at this example. So I've got this 2n plus 3 over 3n plus 2 to the n. Yeah, the nth root of such a term is going to be nice. So let me use the same notation. Take the limit as n goes to infinity of the nth root. The nth root, you remember, is the 1 over nth power. So I'm just going to write it like that. My terms are all positive here, so these absolute values aren't really doing anything, but let me write them so that it matches the notation of the theorem for you. Okay, and then why did I do this? Well, it's because the nth root of an nth power is 1. Yeah, you multiply those exponents. N times 1 over n is 1. I mean, the exponent is 1. When you take the nth root of the nth power, the exponent becomes 1. So I have the limit as n goes to infinity. Everything here is positive. Now you see how crucial all that business in section 11.1 was, because we're going to be computing these limits all the time. This limit is 2/3 by the results of that section. 2/3 is less than 1. So our series, which I'm too lazy to write again, but I will copy it. This series, let me try to write nicely, converges absolutely by the root test. Okay, the root test made that go smooth because the nth root of the nth term simplified so nicely. Let's try another one. This time we're going to be taking a look at the limit as n goes to infinity of the, again, I like to just throw the nth root out there. And then these terms are positive. The absolute values aren't doing anything. And I'm going to rewrite this. Maybe I can do a little side work over here. E to the 2n over n to the n. Well, that's e squared over n all to the n. Yeah, that's why I want to think about that, because I'm going to take the nth root. So I've got e squared over n to the n is an equivalent way to write my term. And now the nth root of an nth power, again, is the first power. So we just get the limit as n goes to infinity of e squared over n. And that's going to be, you know it before I say it, 0. So this series converges absolutely, although that's vestigial in this case because the terms are positive anyway, but it converges absolutely by the root test. Cool. Let's look at a third example. Just kind of showing you each one of these things. I mean, I've already kind of told you everything I know about the root test. If taking the nth root of the nth term makes it easy to take the limit, then use the root test. So I'm just kind of playing around with some different things you'll see here, like this exponent. What is this n squared? I'm going to think about this thing, n squared. Well, what's n squared? It's n times n. And if you want to think about it as exponents, n times n, right? When you take powers of powers, you multiply. So another way to think about 1 plus 1 over n to the n squared, you can think about it as 1 plus 1 over n to the n raise that to the n. Yeah, because you multiply those two exponents together and you get n squared. All right, so we're really stretching the rules of exponents here. But looking at that form over there, if we take the limit as n goes to infinity, I'm just going to write this thing in here first so I have enough room of 1 plus 1 over n to the n, and I take the nth root of that. Well, the nth root of an nth power, just like in the previous two examples, that those exponents multiply together to give 1. So we end up getting 1 plus 1 over n to the n. And is this one in your library yet? You know that limit? It's come up, well, it came up in the ratio test lecture last time. It came up on an activity in section 11.2. I hope you've already written it down, but that limit is e. E is bigger than 1. E is about 2.7. So this series diverges. Oops, didn't mean to bring that line with me. Goodbye, line. This series diverges by the root test. All right, so we'll keep this video short. We'll cut it at just those 3 examples. You can look at some root tests on your activity. You can look at some root tests in your homework. And I will see you when I see you.